All right, so next up we have an early, let me try that again, it's early apparently. We have an early career science highlight of Federico Gasparini.
Hello everyone. I'd like to start by thanking the organizers for inviting me here to present evidence of tropospheric 90-day oscillations in the thermosphere. I worked on this paper when I was a postdoc at Utah State University, and I'd like to acknowledge my co-authors, Maura Hagen and Yusheng Chao. So here's the outline of my presentation. I'll start with some of the background information, and then I'll jump into the data that I've used, in particular the satellite observations and numerical model. And then I'll demonstrate evidence of strong 90-day oscillations in the thermosphere and present evidence of a link to tropospheric convection. And then I'll summarize my results and also kind of list some of the ongoing work. So here we have different layers, the different layers of the atmosphere. I mainly concentrate in the thermosphere, where the sources of variability, we have sources from above, such as the absorption of solar extreme ultraviolet radiation, but also high latitude processes, such as joule heating and particle precipitation. But really in the last couple of decades, evidence has shown that the dissipation of upward propagating waves is a large source of variability in the thermosphere and ionosphere as well. So I'd like to bring up this figure from the decadal survey that shows you the wave coupling in the atmosphere and ionospheric system. And zooming in, you can see in green the lower atmosphere, and in gray the ionosphere-thermospheric system, and in red is the mesosphere. So we have a large number of waves of different spatial and temporal scales, the smaller, finer scale gravity waves, and also global scale waves such as tides and Kelvin waves. And they're being generated by different processes, such as the absorption of solar radiation, but also orographic instabilities and convective activity as well. But important to note is that this, a subgroup of these waves is capable of propagating upwards, and as they do so, they increase, their amplitude increases exponentially with height. And those that are capable of propagating all the way up to the IT system are capable of influencing the general circulation and also couple up in the ionosphere, either in the region, the dynamo region, or directly in the F region. So one of the largest waves that is being generated in the troposphere is a tide, is the diurnal eastward propagating wave number 3 tide, the so-called DE3. Most of you have probably heard of this tidal component. It is mainly excited in the tropical troposphere by the release of latent heat in convective clouds, and also it has been shown to be a large source of variability in the ionosphere and thermosphere. And also it is a large contributor to the observed ionospheric wave 4 cell structure. This figure is from Mlt et al. 2006. Shows the Equatorial normalization anomaly, and you can see these 4 peaks in longitude. They're mainly due to upward propagating waves, and D3 is one of the largest coming from the troposphere. Going into the data that I've used, I used Goche satellite data. This is the gravity field and steady state ocean circulation explorer. It's a European mission. Was launched in March 2009 and re-entered in November 2013. It was on a nearly circular polar orbit, around 260 kilometers. Important to note is that it was on a dawn and dusk orbit as well. It provided global coverage, and for my study I mainly analyzed crosstrack, which are east-west winds, those that are perpendicular to the direction of motion of the satellite. that are being extracted from measurements taken from the accelerometer on board Goche. In addition to Goche, I've also analyzed CHAMP data. This is the Challenging Mini Satellite payload. It's another European mission that was launched in the middle part of 2000 and re-entered in September 2010. It was also on a nearly circular orbit at an altitude of 450 kilometers initially, that decreased to 300 kilometers in the second part of its lifetime. Provided global measurements, and for my study, I analyzed, or I'm going to show results in particular on the cross-track, which are east-west winds, also from an accelerometer on board the satellite. In addition to satellite observations, I've also looked at a numerical model developed by the National Center of Atmospheric Research, the TIME GCM, that's the thermosphere, ionosphere, mesosphere general circulation model. It's a different version of the more commonly used DIE GCM, but it also incorporates the mesosphere. And Hanli Lu earlier talked a little bit about the history of the development of this model. It has F10.7 and KP indices to represent solar irradiative and high latitude forcing. I won't go into details on the model simulation, but important to note is that it gives us estimates of different parameters from 30 to 500 kilometers, and also it has at the lower boundary mirror reanalysis data, which provides a realistic wave forcing. And also the focus of my studies, or the results that I'm showing is on 2009-2010. Now, to represent tropospheric convection, I've used the OLR data, which is outgoing long-wave radiation. This is the infrared radiation that is emitted from Earth and its atmosphere up to space. It is measured by NOAA's polar orbiting satellites, and it serves as proxy for tropospheric convection because the top side of clouds is essentially colder, and so it emits little long-wave radiation. And you can see here some of these convective cells down here. So jumping to the results, essentially looking at CHAMP zonal mean wind data at 330 kilometers, and also D3 tidal amplitudes. And I won't go into details on how I extracted those amplitudes. You can refer to my paper if you're interested. But important to note is that there is a very strong 90-day oscillation that you can see here this is a period versus time wavelet plot at 330 kilometers. And if we look a little bit lower down at 260 kilometers from Goche, you also see there a 90-day oscillation. And if we look at then in the model, zonal mean and D3 data, you also find a 90-day oscillation. You can note that it doesn't occur exactly in the same period of time, and there are reasons for that. I won't go into further details on this. But if we then look at AP and F10.7, you can see that there is lack. There is no 90-day oscillation in the geomagnetic and solar indices, which is an indication that the oscillation is not connected to geomagnetic or solar forcing, but as I'm saying here, ought to be connected to solar and ought to be connected rather to something else, and in particular some internal process. And so to better understand where this oscillation is coming from, I've analyzed the time GCM simulation, which provides data from 30 kilometers to over 300 kilometers. Here is the vertical structure of the zonal mean over time. And you can see a very strong semi-annual variation in the mesosphere. But also you can already note here what looks like a 90-day oscillation in the zonal mean data. You're not able to really resolve that in D3. But if we then take a look at 85 to 95-day filtered version of that data set, we see that there is a very strong 90-day oscillation variation up in the thermosphere that is also present down here in the mesosphere to a less degree. And in the D3, we also see some 90-day oscillation, although it doesn't occur exactly at the same time. Partially, we think that could be caused by the seasonal variation in this tidal component. But really the breakthrough of the study was to look at OLR data. And here I'm showing a time series in blue of OLR calculated as an average of plus or minus 30 degrees of latitude. And down here in red of the time GCM zone of mean winds at 400 kilometers. And you can see in a peridiogram that it shows a very strong 90-day oscillation. And so then looking at a running mean of these data sets, again in blue we have the time GCM winds, and OLR is, in blue we have OLR, and in red we have the GCM mean winds. We find a correlation of 0.71, and if we look at observations with Goche, 0.59, and with CHAMP, 0.63. So in summary, I've analyzed CHAMP and Goche cross-track winds, revealing the existence of a somewhat strong and significant 90-day variation in the thermospheric mean winds with amplitudes of plus or minus 20 meters per second, and also in D3 during a particular period of time in 2009 and early 2010. And then I used the MERA time GCM simulation to demonstrate that this oscillation is coherent with height, and it's not really propagating as a wave from below. And also analyzing the outgoing long wave radiation data, I revealed a similar 90-day oscillation in tropospheric convection, and also found that there is correlation with the observed and modeled thermospheric winds. A similar but localized 90-day oscillation has also been shown to exist in mesospheric temperatures. I'd like to acknowledge Yu-Cheng Shao at Utah State, who actually introduced me to this work in the first place. In summary, we believe that the physical process responsible for this 90-day oscillation in the thermosphere could be due to tides and gravity waves in the lower atmosphere that are being modulated by 90-day oscillation in tropospheric convection, and they're imprinting this oscillation into the thermosphere by energy and momentum deposition. And so my study really shows that there is a strong connection between the troposphere and the thermosphere on intraseasonal timescales. But it also raises important questions, and here I'm just listing a few that I'm working on right now. So the first is how frequent, prevalent, and persistent are correlations on intraseasonal timescales between the troposphere, the mesosphere, and the thermosphere within the past 15 years when we have the CHAMP and Goche data. And also, how does the newly developed WACA-MAX 2.0 capture this intraseasonal variability, but also what physical insights really the model can give us. And lastly, the third is what plausible roles do large-scale upward propagating waves really play in coupling intraseasonal variability from the troposphere up to the thermosphere. There are, of course, a lot of other questions. For example, is there a connection to the ionosphere since the winds are so strong? And also, can we find a connection to the MJO as well? So just to wrap up with the acknowledgements, I'd like to acknowledge NASA that supported me at Utah State University where I conducted this study. And again, thanks to Yu-Cheng Shao. And if there are any questions I'm not addressing here, I'll lift this up and you can email me at that email address. Thank you.
I think we do have some time for questions.
One question.
Maybe one, okay.
Thanks for the interesting talk. I was just wondering, in the ionosphere and the thermospheric studies, we talk about the semi-annual and annual variations. Now you talk about the 90-day oscillations. Are there any difference between these two kind of activities, oscillations?
Well, the 90-day oscillation has never been shown to occur really in the thermosphere. So we're not sure if that could be, if the 90-day oscillation could be related to, since we know that the tropospheric convection has a very strong 90-day oscillation in it, and that's an indication that it could be perhaps related to the MJO. And so we are trying to see if if there is a connection to the MJO in the thermosphere. In terms of a connection to the semi-annual annual, there isn't that we are aware of. One point that some other people have raised before is that the 90-day oscillation could be thought as a modulation of a 60-day oscillation and the semi-annual variation at 180 days. But in this period of time, we don't see any 60-day oscillation in it. So we are, because of that, we know that it's not a simple superposition of two different oscillations of longer and shorter period.
All right, thank you. Hi. Thanks for that talk. Could you go back to your bullet points? You had 5 bullets 2 slides ago. This one.
Oh.
Your final slides, where your summary slides. Second one.
Yes.
Demonstrate that this oscillation is coherent with height and is not propagating from below. So that would say, okay, it's not propagating from the troposphere, but then you said it is related to the troposphere. So could you help me understand what I'm missing?
Sure. So what I mean here with this is that essentially looking at its vertical wavelength, we do not see the typical downward phase progression that would be associated with the propagation from below. So what we think is happening is a modulation in the troposphere of gravity waves in particular, but also tides, and that's why I focused or showed results for the D3. So we think that these waves are of shorter period, are capable of actually propagating up to the thermosphere or lower thermosphere, where they dissipate and impart the 90-day oscillation into the mean flow, but not as a traditional wave that is propagating from below. And we analyzed, the model simulation allows for, we have all local time and longitudes, and so we can actually calculate the phase speed of the wave, and there is none in the lower atmosphere. Thank you.
Thank you. So next we have our poster award presentation by the head judges, Susan Nassel and Lauren Cheng.
Sorry. Okay, hopefully everyone's awake now with all that noise. Is that gonna slide on? I think it'll be fine. Okay, oops. Okay, so good morning, everyone, and on behalf of the Science Steering Committee and this year's poster judges, I'd like to present the results of this year's Student Poster Competition Awards. So first off, this year we had a lot of really great posters, both in the MLT and the IT sections. We had close to 100, and just going over the posters, it was very inspiring and interesting to look at some of the most recent results that CEDAR students are presenting and are working on. And we'd like to thank everyone who participated in the student poster competition and for sharing your really interesting results. I'm sure that there's going to, that for a lot of you, you will be, that your results will bear fruit and produce very exciting publishable results over the next couple of years. Now, in order to evaluate these 100 or so posters, several members of the community volunteered their time, effort, and expertise to provide some comments and evaluations. And this year, our judges put in a lot of extra time and effort to provide comments on the student posters that were received. Our judges provide comments on what was done well, what could be improved, and based on some feedback we've received from our students, we've also tried to provide information on perhaps papers that are relevant to the topic being presented, as well as experts on related subjects. So to the students who participated in the student poster competition, I'd like to let you know that the judges' evaluation forms are available to you. They are right outside this hall right now at the registration desk. And we encourage you to pick up the evaluation forms and perhaps take a look at some of the comments the judges have provided. Now, again, several members of the community dedicated their time and effort to going over a lot of different posters. We wanted to correct for biases and receive as large a sample set as we possibly could. So again, some 32 members of the community donated their time and efforts, and we spent a long time going over posters, looking up the digital versions you guys uploaded, talking to you in person, and then spending a lot of time in De Vargas, just down the hall, engaging in philosophical debates, the occasional fist fight, and by the end of the night, we finally were able to narrow the list down to the top 3, and based on the same criteria, if an undergraduate made it to the final short list, we will also be presenting them with an undergraduate poster award.
There were actually no lists.
Okay, well, anyhow, so again, it was very difficult, but somehow we managed to narrow the list down, and we'd like to recognize the students who were determined to have very exciting results and very good presentation. So I'd like to start, first of all, by thanking and acknowledging all the judges and the supporting personnel in the student poster contest. This is where I blow the cover of all the judges in case it wasn't that obvious. So I hope you will please join me in thanking all the judges with a round of applause. Thank you. And I'd like to encourage the members of our community to please consider serving as a judge in future CEDAR student poster competitions. It's a very valuable, service to the community and very valuable information that we provide to the students in keeping them interested and encouraged in our field. So I'd like to start with the Mlt Poster Awards. So this was the poster session on Tuesday. So I'd like to start with the Undergraduate Award, and as I announce the awardees, I'd like to invite you to come up to the stage and be recognized. So for the Undergraduate Award for MLT, this goes to Gabrielle Gutormanson from Boston University. Gabrielle, are you here? Okay, please come on up. I'd like to mention that everyone was evaluated on the same criteria, so if an undergraduate made it to the final round, that is definitely an effort worthy of recognition. Okay, next is the honorable mention for the MLT Awards. The honorable mention goes to Komal Kumari from Clemson University. Komal, are you here? Yep, come on up. Next, second place for MLT. Second place goes to Zhiting Xu from National Central University. And then first place for the MLT session. First place goes to Gonzalo Cucho Padin from UIUC. Okay, congratulations and excellent work. So moving on to the IT section. Let's start again with the Undergraduate Award. So the Undergraduate Award in the IT section goes to Robert Irvin from Purdue University. Okay, excellent work, congratulations. We hope you consider grad school. Okay, next, for honorable mention, for the IT section, honorable mention goes to William Longley from Boston University. Okay. Congratulations. Okay, so yeah, we had to get an ISR one in there. So let's see, second place for IT section goes to Xingyu Zhu from University of Texas at Arlington. Congratulations. And finally, first place for the IT section goes to Hannah Holt, University of Colorado. So congratulations on the excellent work. We hope to continue to see you at future CEDARs, and we look forward to seeing your future results. So thank you very much, and again, I'd encourage everyone who participated in the poster competition this year to please come back next year. A lot of this work is iterative, and I'm sure that you'll have a lot of really exciting results next year. Thank you very much.